Okay, let's do another example. Slightly different one this time. Rate of radioactive decay. So a sample of radon initially undergoes 7.0 times 10 to the 4 alpha particle disintegrations per second. After 6.6 days, it undergoes 2.1 times 10 to the 4 alpha particle disintegrations per second. What I want to know is, what is the half-life of this isotope of radon? Now, when it comes to radioactive decay, we are dealing with a first-order process. Now, this makes life very straightforward, because in the end, what I want to calculate is the half-life. And that's equal, if it's a first-order process, to the natural log of 2 divided by k, where k is your rate constant. In the lectures I said if we type in the natural log of 2, we end up with 0.693147118. Now, as far as I'm concerned, we can shorten that to 0.693 over k. So clearly, we are going to have to calculate k somehow, and that's when we use the integrated first law. Now, in this case, what we've got here is the natural log of A equals minus kt plus the natural log of A0. Now, what do these A's and A0s, or what do all these things mean? Well, A is about activity, and in this case, it's the activity of our sample at time t, which in this case is 6.6 days. And we know from the question we're dealing with 2.1 times 10 to the 4 alpha particle disintegrations per second after 6.6 days. So that's going to be that figure. For A0, that's our activity at time 0, our starting activity, if you like, which in this case is 7.0 times 10 to the 4. So I'll put that, that's our start. T, well, that's time. In this case, is 6.6 days. 6.6 days. K is effectively our rate constant. That's what ultimately we're going to try and calculate. So what I'm going to do is take the integrated first law and break it into bits. So to start off with, I'm going to rearrange this equation to make minus kt the subject. Now if I do that, minus kt equals the natural log of the ratio of our activity at time t divided by our starting activity. So what I'll do is I'll plug those numbers in. So our activity at time t is 2.1 times 10 to the 4 disintegrations per second. Our activity at the start, well, in the question it tells us is 7.0 times 10 to the 4 disintegrations per second. If I divide these two numbers, it's going to be a ratio, I'm going to get a value of 0.3. So if we just tidy this up a little bit, minus kt equals the natural log of 0.3. Now we're getting somewhere. So what I'll do now is I'll start playing with the logs. So I'll sort this number out. Natural log 0.3 gives us a value of minus 1.20. So tidying it up again, minus kt equals minus 1.20. Now I feel confident enough to make k the subject. So I'm not interested in the minus, I'm not interested in the t, but we just can't ignore them. So we've got to do something with them. So that k, I'll bring it down here. K is now the subject. And that's going to be equal to, mustn't forget about that minus, pop in a bracket, minus 1.20 over t. Now that t, as we know, is 6.6 days. So let's tidy it up again. K equals minus 1.20 over 6.6 days. So if I get the calculator out, put in that minus first, open up a bracket, minus 1.20 divided by 6.6, close that bracket, equals plus 0.18. So now I have a value for k. Going back here, remember what our half-life is? 0.693 over k. So let's just sort that out. Our half-life will be equal to 0.693 divided by 0.18. Let's have a look what the calculator tells us. Divided by 0.18. 3.85 days. So the half-life of radon is 3.85 days.